In the Dumas method of determining the molar mass of a volatile liquid, we'll start out massing an empty 125 milliliter Erlenmeyer flask, a small piece of aluminum foil, and a small piece of copper wire. We will then add approximately 5 milliliters of the unknown liquid. We will cover the mouth of the flask with the aluminum foil. We will use the copper wire to hold the aluminum foil in place. We will place a small pinhole in the top of the aluminum foil. We immerse the flask in a beaker of boiling water. The liquid inside the Erlenmeyer starts to boil and vaporizes. As it vaporizes, it pushes air out of the pinhole. Eventually, all the liquid vaporizes and the flask is filled with just enough vapor to fill the flask at the temperature of the boiling water. Once the liquid has completely vaporized and the vapor has reached the temperature of the water bath, we will remove the flask from the water bath. The vapor inside the flask will condense to a liquid. When the flask is cooled to room temperature, the liquid that has condensed was the amount of vapor that would fill the flask at the temperature of the boiling water bath. We will now mass the flask, the liquid, the aluminum foil, and the copper wire. Since we know the mass of the empty flask, aluminum foil, and copper wire, we can get the mass of the liquid. We will determine the volume of the flask, which is also the volume which the vapor occupied at the temperature of the boiling water bath. We'll remove the copper wire and the aluminum foil. We will fill the flask completely with water, and we will pour the water into a graduated cylinder. We will record the volume of the water.
Jump there. So now let's talk about what we would have seen in the pre-lab lecture and what you would have seen in the actual lab. So the first thing I would have had you do is bring me a dry 10 milliliter graduated cylinder, and I would have you take a piece of tape and put your name and your partner's name on there. So you'd be getting an unknown substance that you would find your molar mass from. And we have these special Dumas flasks, and these are the ones that you see right over here. And they're very cool and very hard to get, also very breakable. So I would have impressed upon you to always walk around the room with your partner when you are holding this to make sure nobody bumps into you and you don't accidentally drop it. So this is where I usually tell my joke about imagine that you're in that junior high school class and you're learning how to be parents and your lab partner is your co-parent and you are have this little egg and this is your little baby, and I encourage you to name it and care for it so that as you're walking around the room you would never ever drop little Joey or whomever you have. All right, so what you would also do is set up a water bath. So on the ring stand, so you would get a ring stand here from the back of the classroom, and then you would set up an actual ring on top of it and then the wire mesh, and on top of that you would be placing your beaker. So here this beaker would sit right on top, and we would fill it about 2/3 to 1/2 full with tap water. You would weigh your flask empty, and then you would put about half of the unknown that I'm giving you into the flask. So I'm giving you enough for 2 trials, although today you're going to get data for 3 trials, but in lab you normally only have 2 trials. And so once you put about half of it in there, you will set up your experiment like so. So here is the ring stand. Here's your ring, your wire mesh. You have your Bunsen burner underneath that's heating your water bath. And inside the water bath, you've got your Dumas flask, which is clamped. And it has a very small opening. And through that opening, you would see gas escaping. Now, what I would tell you to do is keep on heating until you don't see any more gas escaping. And for several years now, we always struggled to figure out a good way to show you when the gas is done escaping. And it was actually a student that came up with this really brilliant idea, and we have stolen her idea every semester since. So what we have you do nowadays, thanks to that industrious student, is, let's see, oops, I'll get that later, okay, is what you would do is you would take your cell phone with the camera light and you would shine the light right here onto the steam, and then you would look at the back wall of the fume hood, and you can actually see the steam moving around on that back wall if you shine the flashlight from your cell phone on it. So it's actually a great way to see when the steam stops. Before, we used to try to get you to look right here and see when the liquid goes away, but you're trying to look through a beaker of water to see if there's any kind of liquid or something that looks like water inside your flask, and it was so miserable. Everybody had trouble seeing it. So this great idea about looking through your cell phone, looking with your cell phone flashlight onto the back wall and watching the shadow, it works really, really well. So the idea is that the gas is going to escape for a while, but after a while it stops. And when it stops is when the pressure of the gas inside the flask is equal to the gas in the atmosphere. The idea is the atmosphere is pushing down on your gas and your gas is pushing back up. So long as there's more pressure inside of your flask, it's going to go out, it's going to escape. However, once the pressure is equal, you're not going to get any more escaping gas. So that's why the gas actually stops escaping, and that is when all the liquid is vaporized and you just have pure gas in your flask. There we go. All right. So once that happens, you would have to very carefully take that Dumas flask off the clamp, out of the water beaker, and you'd have to get it over to the sink. Because what we do is we use the sink to cool it. So what we would want to do is run some cool water over the sides of the flask, but of course not in the top. So we would have either you or your partner put a finger over the top. It's a very small hole, so somebody holds their finger over. The other person is washing the baby, giving it a nice bath, drying it off. And it does need to be dried because we don't want that water weight to interfere with the weight of the flask. We also don't want any water on our balances, and it really is a two-person job because one person's got to hold and put their finger over the hole on the top, and somebody else is rinsing and drying the baby. All right. So once all of that happens, then you're going to take it over to the balance. And we do usually ask you to keep your finger over the hole until you get into the balance room and you're ready to weigh it. Now the cork is a challenging thing because the cork has to come off. This cork right here has to come off when it goes onto the balance. And you got to be really careful because as you're pulling the cork off, sometimes little pieces do fall into the Dumas flask. But luckily that's not a problem that any of you have. All right. So here are my usual instructions, being really careful, never hold it by the cork or the neck, always supporting it on the bottom with a hand or cool wire mesh. You're going to weigh the dry flask and add about 3 milliliters of your unknown. The way you would know that you've added 3 milliliters is because it's already in a graduated cylinder. So we would have given you a pipette, and so you just draw out approximately 3 milliliter. You heat it, and then you cool it off by running cooled water over the flask in the sink with a finger over the opening, and you're recording the temperature just like they did in the video of the boiling water. We are assuming the gas is the same temperature as the boiling water. All right, so dry the outside of the flask, and then you weigh that flask dry, and your finger should stay over the opening until we weigh that flask. And we want to take the first number we see, just in case a little bit more evaporates. Sometimes the mass starts to go down. All right, so the waste would go into the waste container, although if we have time to do a second trial that same day, Then I would have you pour in the rest of the unknown from the graduated cylinder, do the same process a second time, and then when you're all done, your waste would go into a waste container, and you would get to dry the inside of the flask by inverting it over a tube with warm air. So some of you actually saw our gigantic air heater we have in the back corner of the lab. So that is the one that we use our Fisher burner for. That Fisher burner goes to over 1,000 degrees, over 1,000 degrees Celsius. It is enough to actually melt a rock salt, which is pretty cool. Your Bunsen burners can't do that. But we set that up, and we have a tube on there that kicks out nice warm air. It's actually nice to warm your fingers. But what you would do is you would put your flask upside down, and I say for approximately 1 minute, but for most people, it's going to dry almost instantly. So you put it upside down, and there's a little ring right here to support your flask. And once it's dry, you would bring it back up to me. I would take a look at it, and then we would put your stuff away. So it's a pretty simple lab. It's actually a really fun lab, so I'm sorry you guys won't get a chance to do it. On the upside, nobody will break any glassware, and that glassware is really hard to replace. But any questions about the experiment or about what you would have done in the lab? All right. So next up, let me show you briefly your sample data, and this data is already loaded onto Canvas for you, so it's in the lab notes section. So just like always, I want you to copy this down to your own data sheet in pen. So each of our flasks have a letter to them, or I should say a letter or a number. This particular flask is flask letter V, and there was a piece of paper that was on the bulletin board in the room, and you would look up your flask and then find the volume of it. So while it's true you could have used the method that they did in the video, we prefer to just tell you what your volume is, and that's because these flasks are very, very delicate. They have a very small opening, also because we're trying to keep them as dry as possible. So you would just look up the letter or number of your flask and find the volume. So here, all three trials use flask letter V, and they all have a flask volume of 298.5 milliliters. The pressure in the room is 761.9 in this fictional experiment that everybody's doing. And the mass of your empty flask is going to be 239.2510, and that's going to be in grams, and that is for every trial because you use the same flask for each trial. And now at the end of your experiment, notice you have 3 different experimental values here. So each trial you got a slightly different mass. And then from here you'll do your calculations, which I'm going to show you in just a moment. But any questions on the data? All right. So here is my calculation page, and you're going to notice that I labeled A and B. So A is the empty flask, B is the flask plus the condensed liquid. And I know students sometimes freak out at that point because I tell you to heat it until it's all gas, but as soon as you pulled it off of the boiling water, it goes back to liquid. So sometimes people would take it off and they'd see the liquid and they try to put it back into the hot water bath. But it's supposed to go back to liquid because the room temperature is cooler than the temperature of your flask. Oops, and I think, did I forget to give you a temperature here? I forgot to give you a temperature. I need to add in a temperature. I will add it in here and then I will repost this. I apologize. So let's say that your temperature So this is your temperature of your boiling water. I'm going to call it 101.2 degrees Celsius for all trials. In real life, each trial would probably be a slightly different temperature. And if you're wondering, hey, how could it be 101.2? It's supposed to boil at 100. Sometimes in the lab, we find it boils just slightly higher, and that is because we get a little bit of particulates in our beaker, so it's normal for it to boil just slightly higher, sometimes in a lab situation, especially if we're using tap water instead of distilled water. All right. So here, temperature with 1 digit after the decimal. And here for the results, I've numbered them 1 through 5. All right, so number 1, mass of flask plus liquid minus mass of empty flask. So this is B minus A. So in other words, if we want to know how much of that compound was in your flask at the end of the experiment, you're going to subtract these two right here. So the flask with the compound minus the empty flask, that gives you the mass of the unknown, how much stuff is actually in there in grams. So any questions on number 1 there? All right, so next up 2. So 2 wants to know the moles of your unknown. So you're going to use your gas law skills, PV equals nRT, and you're going to solve for the number of moles. So let's take a look at your pressure. So pressure right here is in torr. Make sure you convert that to ATM because your R involves ATM. Your volume is right here in milliliters. Make sure you convert that into liters because again we need liters for our PV equals nRT. N is what you'll be solving for. R is your constant. And your temperature, which is right over here, make sure you convert that into Kelvin. All right, then you'll solve for moles, which is your N. So any question on number 2 about how you're going to plug into the PV equals nRT to solve out for your number of moles? All right, so number 3 asks for the molar mass of your unknown. What you're going to do is take the grams that you found and divide it by the moles. So in number 1 here, you found the mass of your unknown in grams. And in number 2, you found the moles. So you just need to take grams, which is number 1, divide by moles, and that gives you your molar mass. And that calculation is right over here. So any questions on that molar mass calculation? All right, so next up is percent difference of the molar mass. Ooh, and we have 3 trials. You know what? I'm going to shorten this. I'll make your life a little easier. I'm going to shorten this to 2 trials because otherwise getting the percent difference would be a little challenging. It'll be a lot more work actually. So let's make your life easier, not give you any more work than you would have had in the regular semester. So I will re-upload this with just the 2 trials and the temperature for all trials. All right, so percent difference is going to be trial 1 minus trial 2 divided by your average. And remember, average is trial 1 plus trial 2 divided by 2. And then you'll multiply that by 100. And in case you don't recognize them, these lines right here are called absolute value bars. And what that means is just report your percent difference in a positive number. Even if you get a negative, just throw away the negative and report it as a positive. All right. And again, the average, trial 1 plus trial 2 divided by 2. So this right here goes to your average. But you also report your average separately as number 5. So the calculations on this lab aren't too bad. But any questions on anything here for any of the calculations for the lab itself? All right. So next up, the discussion questions. So I let you skip A, B, and C because A, B, and C, the way they're written, it's just kind of tough to figure out what they're actually asking, and they're asking you to derive an equation, and I think that's a little too much. So we're just going to do letter D, but notice letter D has 1, 2, 3 parts to it, and I do want you to show your calculation. So just like always, you can do it on a piece of paper, take a picture, and upload it. And these are all things we've done in class. So here you get grams of unknown organic compound, and you know the volume, the pressure, and the temperature. So here you're going to find its molar mass, just like what you did up above when you found the molar mass of your unknown. Then it says on analysis, it has this much carbon, this much hydrogen, and the rest is nitrogen. You're going to find its empirical formula. So we've done, yes, and I see from Maria, we are only going to do the 2 trials. So I'm going to re-upload that. So if you've already printed it out, just X through the trial 3. All right, so here it's an empirical formula question, and we've done a lot of empirical formulas, but where students get stuck sometimes on this one is the rest is nitrogen. So if you know how much carbon and how much hydrogen there is, how are you going to figure out the nitrogen percent? Any thoughts? Yes, add and subtract from 100. Exactly. Exactly. So you're going to take 100, subtract 49.3, and subtract 12.3. So any questions about how to figure out the percent of nitrogen in there? All right. And then finally it says determine the molecular formula and the true molecular mass for the unknown substance. All right. So here you know the, you're going to know your empirical formula, and you have its approximate molar mass. So you're going to use that molar mass that I just circled to find N. I know we have way too many N's in this class. So N, remember, that was the molar mass or molecular mass. Divided by empirical formula. So it's the full mass, which you found in part 1, divided by the empirical formula mass. And then you're going to take N times the empirical formula. For example, if you find N to be 2, then you're going to double everything. If you find N to be 3, you're going to triple everything. So any questions on anything there for finding the molecular mass? Okay, so now where students sometimes get turned around is the true molecular mass. So you have found up here the experimental. So the experimental molecular mass, and it should be somewhere near the true molecular mass, but it's not exactly the same. So once you find your formula, let's just say, for example, that your formula is, I don't know, C5H10N. Let's just imagine that's what it is. The way you're going to find the true molecular mass is you're going to go to your periodic table and do 5 times carbon plus 10 times hydrogen plus nitrogen. And again, it should be close to what you found in number 1, but it may not be exactly the same. So I know part 3 of this gets a little tricky, but any questions about this idea of the true molecular mass, that you will find it from the formula that you get? Okay. All right, so questions about anything that we've talked about here?